Hello everyone. Today we'll start our discussion on chemical equilibrium. Now, in this lecture, we'll cover the what happens when several systems, reactants and products are in equilibrium and a chemical reaction is happening. What happens to the how we can predict the spontaneity or the directionality of the chemical reaction, and what happens to the reactant mixtures, like what happens to the concentrations of the reactants and the products when equilibrium is attained. Now, to begin with, we'll define a quantity advancement, but to understand why we need an advancement, let us consider a particular situation. Suppose we have a reaction which we are writing as a nu A. Nu A is the stoichiometry of the reaction, plus nu B of B, plus this way, and suppose it is in equilibrium with C and D. Say nu C of C and nu D of D. Now, when we discuss the rate of the reaction or the kinetics of the reaction, we'll use the similar concept. Now, let us take an example. For example, say hydrogen and oxygen forms water, and you know that the balance equation will be 2H2 plus O2 is 2H2O. Now, suppose I talk about how much reaction has proceeded in say 1 minute, and say for example 100 molecules of oxygen has been consumed in that in the 1 minute duration, and we are saying say how many number of hydrogen will be disappearing in 1 minute. That will be 200 times, of course. Now, in order to ask this question, how much the reaction has proceeded, if you look from oxygen's perspective, it is 100 molecules. If you look at hydrogen perspective, it is 200 molecules. So we need to actually quantify the extent of the reaction independent of the constituents, like whether it is a hydrogen, whether it is a oxygen, something like that. And also you could actually explain the extent of the reaction based on the products also. In 1 minute, we see that again 200 number of molecules are produced. Now, from the reactants perspective, if we say, then we will see that this number of molecules has been reduced. So we can actually use a negative sign for that. But from the products perspective, it is actually positive, because those number of molecules has been generated. So we have to, in order to maintain a consistency, that how much reaction has proceeded, one has to keep those things in mind, whether it is a reactant or the products and the stoichiometry. But if we want to get rid of all these things, so whether it is a reactant or whether it is a product or it is independent of the stoichiometry, we want to find something which will tell the extent of the reaction in 1 minute, how much the reaction has happened. That quantity will be independent of whatever we are choosing, like whether it is a reactant or whether it is a product. And that quantity we call as the advancement or the extent of the reaction. So we call it as a extent or sometimes advancement of a reaction, and we denote it by a symbol, and the symbol is a Greek letter. It is called xi. So xi is denoted as the advancement of a chemical reaction. Now, to give you an example, suppose for example I have some amount of say for 1 minute I say that the reaction has proceeded by xi amount. So which means from reactants perspective, say hydrogen's perspective, the number of moles that will be present or not, that will be consumed, say at time 0 we had say H2 concentration was something like H20, oxygen concentration was O20, and water concentration was say H2O 0. So the suffix 0 means actually the at time 0. Now similarly we can ask this question that at time t, suppose the reaction has proceeded by xi amount, that is the extent of the reaction. So here the amount of hydrogen after that specified time will be nothing but H20, and then it will be negative of, because I'm using negative because it has consumed, negative of 2 times xi. Similarly for oxygen, it has also been consumed, so it will be oxygen minus xi. So it is the stoichiometry including the sign, whether it is a reactant, we'll consider it as a negative sign, and if it is a product, it will be the positive sign. And for water, we can say that it is H2O initial concentration plus 2 xi. So xi is actually independent of whether it is a reactant or the product. The total amount of the reactant or the product, which is at time t, will be either reduced or increased, but that will be proportional to xi, and that proportionality constant will be just the stoichiometric constant including the sign. Now then we have defined a quantity which is very much independent of the reactant or the product, and that basically tells how much the reaction has advanced. So that's why we call it as advancement or the extent of the reaction. Now let us say that we have in that notation that we are writing it. Suppose the initial amount was Na0, so we can write it as Na comma 0, and similarly nu B was Nb0, nu C was Nc0, and nu D was Nd0, and then we can say that how much amount stoichiometric amount has been remained, how much amount is remained at time t. So this will be nothing but minus nu A into delta xi. Suppose I'm calling this as delta xi amount has been reduced, or delta xi is the extent of the reaction in an interval say delta t. So similarly from Nb's perspective, it will be Nb0 minus nu B into delta xi. From Nc's perspective, it will be Nc0 plus nu C into delta xi, and from Nd's perspective, it will be Nd0 plus nu C nu D into delta xi. So delta xi is the advancement in delta t time. So we can ask this question, fine, so what is the free energy that is associated, or what is the free energy change that is associated with this reaction? So we know that the amount which we are talking about is nothing but the Gibbs free energy, which we can write it as a delta G. Now we already know that delta G is nothing but minus SdT plus VdP plus mu I dni, or sum over the mu I dni. So that we can write it mu I dni. So that is basically the amount. Instead of delta G, you can write it as dG. Now we are asking this question, what is the amount of dni? Now if you think from this equation, we can easily calculate what is the amount of dni. So instead of the delta notation, we can just use say at time t we had xi advancement, just like we did it for in the example of water, and then now we can differentiate. So this was at time 0, and if you differentiate it, you will see that if I differentiate every quantity, what will be left with is this thing, because Na0 is constant, Nb0 is also constant, similar for Mc0 and Nd0. So what I'll be leaving left with for the reactant A will be minus nu A dxi for dni. So what will be what we can write it is nothing but minus HDT plus VDP plus sum over I, and we can write it as say in this case it will be minus mu A dxi minus mu B into dxi plus mu C, I'm just taking the summation, into dxi it will be basically minus mu A, it will be minus nu A, or we can write it once again as in terms of mu and I. Let us just use the same notation, sum over I, it is mu I into the stoichiometry, which is nu I including the sign, remember, and then it will be nothing but into dxi, because I'm just taking the derivative. So what we notice here is that at dg, if I take the derivative with respect to say dxi, that will be nothing but the difference between the all the reactants and products. Let us just expand it and then it will be clear. So what I'm saying here is that it will be minus HDT plus VDP plus, now we will expand, we have mu A and nu A, but nu A was a minus sign, remember, so it will be minus nu A dxi minus, we will have say mu B dxi plus we will have mu C because mu C had a plus sign into dxi plus we will have mu D into nu D into dxi. So if I take this derivative delta G del G del xi at constant pressure and temperature, then these two terms vanish because I'm taking constant pressure and temperature. So I'll be left with mu C plus mu D nu D minus mu A nu A minus mu B nu B. So that quantity. Now let's think for a moment. Suppose we had a very simple reaction like A is going to B, and this is an equilibrium reaction. And so what is happening here in that, so in this case A is the reactant and B is the product. So this del G del xi at constant pressure and temperature, that will be nothing but it will be mu B minus mu A. You can easily figure that out. So what I'm doing is that I'm taking basically the difference between the Gibbs free energies, and the difference is taken from the reactant Gibbs free energy minus the product Gibbs free energy. So what I see is that this difference I can actually call as some difference in the Gibbs free energy when the reaction happens. So you can call it as a reaction Gibbs free energy, and we denote it as delta G, and since this delta corresponds to some reaction, we put a suffix R here. So reaction Gibbs free energy is defined as the derivative of the Gibbs free energy with respect to the advancement of the reaction at constant pressure and temperature. Now the question is whether the reaction will be spontaneous in this direction A to B or the reverse direction is spontaneous. That we can easily figure out. So if A to B is spontaneous, then this direction is the forward direction. Then we'll see that the delta GR should be negative, because we know that at constant pressure and temperature, the changes in Gibbs free energy, if it is negative, that gives the direction of spontaneity. And in this case, if that is so, then the B to C direction, or the B to A direction, I should say, for that actually the delta GR, if that is say more than 0, it is positive, then actually it is not spontaneous. But what happens here is that we are not talking about one particular reaction going in the spontaneous or non-spontaneous reaction. What we are saying is that the overall reaction Gibbs free energy must be negative. Now what it means is that if we want to plot the Gibbs free energy versus the extent of the reaction, so then we'll see some curve like say this. And what it means that for the reactant, when A is going to product, I'll have a slope which is negative. Now this slope is nothing but, what is the slope of this curve? The slope of this curve is del G del xi at constant pressure temperature, which is nothing but by definition is the reaction Gibbs energy. So if the reaction Gibbs energy is negative, then which means the slope is negative, so A to B is actually taking the reaction towards forward direction. However, if the reaction Gibbs free energy slope is positive, which is B to A, then actually it is actually taking it to the non-spontaneous direction. So what will happen at both these, so here actually what I'm saying is that del Rg, sorry, the suffix R should be here, and del Rg, if it is greater than 0, the curve will be like this, and del Rg, which is less than 0, the curve will be like this. And what is happening here, the forward reaction is happening, then the reactant, it's gaining in amount, more and more B is formed, so the B is actually giving vacuum to A. And then what will happen, these two Gibbs free energy, as we have seen, that they will actually try to minimize the overall Gibbs free energy, which is something like this, because we know that the overall Gibbs free energy has to be minimum. Now delta Rg greater than 0 or delta Rg greater than less than 0, those are basically two sides of the total Gibbs free energy, which is basically downhill slope, and one is basically negative slope, one is basically positive slope. And then when the equilibrium is attained, we know that the changes in Gibbs free energy must be 0, because you can also see that the slope has been it's a flat, it's basically parallel to x-axis. So we can say that at that point the delta Rg is 0 here. So at equilibrium, when the equilibrium is attained, the Gibbs free energy or the reaction Gibbs free energy change will be 0. So what we in a long story short, what we have said is that suppose you start with a not a mixture, say suppose you start with A only. So what will happen, initially A will form B, but as soon as the B concentration is increasing, B is also forming A. Now the changes in the Gibbs free energy, for one case actually it is decreasing, and in one case it is basically increasing. V2A is basically increasing. So what will happen is that V2A is also actually a reaction, but when we have the reaction free energy, when we discuss the slope of the Gibbs free energy with respect to the advancement of the reaction, then we see that for these two reactions the slopes are either positive or negative. And the positive and negative slope means actually they tend to push the reaction towards a region where the delta G of the reaction, which we write as delta Rg, will be 0. That's the concept of reaction gives free energy. And when it is zero, the equilibrium has been attained. Now, we already discussed that this gives free energy, the reaction gives free energy, is the difference between the reactant and the product. And we have already argued that this delta Rg is nothing but mu B minus mu A, which is basically the differences in the Gibbs free energies, differences in Gibbs free energies. So the difference is taken from product minus reactant. It is product minus reactant. And if we do it in this way, we see that the reaction Gibbs free energy is nothing but the differences in the chemical potential of the reactant minus product. Now, in the general case, as we have seen, that these chemical potentials has to be multiplied by the quotients. So it is obvious, because you have to, if you have a different number of moles for B and A, you have to also take that into account. And that's why in the general case, we have to also multiply it by the reaction, reaction quotient. That will be, exploring now. But before that, let us discuss a very general case where we are saying that that any chemical potential, say mu, of any species, we can write it as mu0 plus, say, RT ln P. And remember that this P is nothing but P by P0, because we have to always say that it is taken with respect to a standard state. But usually we write it as P. Now, for any ith constituent, we can write it as something like this. And this Pi, instead of Pi, we can write it as Pi by P0. But if I don't write, so it inherently means that we have divided it by P0, where P0 is the standard state, which corresponds to 1 bar pressure. Then in many cases, actually, the standard states used to be like the 1 atmospheric pressure, but we will use the SI convention, where we are using 1 bar pressure. Now, let us again take a very general argument. Like, we'll see what happens if I include the nu C, nu D, all these cases. But for the timing, let us say stick to this particular reaction where the stoichiometries are also 1:1. Now, for this reaction, we already know that the reaction Gibbs free energy change is nothing but mu B minus mu A. Now, we can expand it using this equation. So we can write it as mu B, instead of mu B, we can write it as mu B0 plus RT ln PB. So let us use the full form, PB by PB0. And similarly for mu A, we can write it as mu A0 plus RT ln, we have PA by PB PA0. So we can now take the terms common, which is mu B0 and mu A0. So it will be mu B0 minus mu A0, which is the difference of the chemical potentials taken at the standard state, plus we have RT ln, and remember that ln A minus ln B is nothing but ln A by B, and when you do that, the P0 terms cancel, and so you'll be left with RT ln PB by PA. And when now equilibrium is attained, so you will have this term is equal to 0 only when equilibrium is attained. Now, before that, we can actually call these ratios as the reaction quotient. We write it as mu B0 minus mu A0 plus RT ln Q, where Q is known as reaction quotient. So Q is nothing but at this moment is the ratio of the pressure of the products divided by the reactants. But we will see that if I have stoichiometric numbers which are not equal to 1, what will happen? We'll discuss the more general case. Now what we found so far is the reaction Gibbs free energy is given by mu B0 minus mu A0 plus RT ln Q. Now at equilibrium, we know that the reaction Gibbs free energy must be 0 because the slope of the del G del Xi curve was horizontal with respect to the x-axis. So we'll have mu B0 minus mu A0, that is RT ln Q. Now look at this equation. Usually the delta Rg is nothing but mu B minus mu A. So if we have a quantity which is mu B0 minus mu A0, we can call it as the standard reaction free energy. So instead of that, we can write it as standard reaction free energy plus RT ln Q. And at equilibrium, remember that this Q is now at Q at equilibrium. This is also Q at equilibrium. It won't be the same Q as which is the general case. So what we found is that delta Rg0 is nothing but minus RT ln the reaction quotient at equilibrium, but instead of writing it as Q equilibrium, we write it as K equilibrium. So where K is known as the thermodynamic equilibrium constant. We call it as a thermodynamic equilibrium constant because we'll see that there are also usually for when we describe, say, the reaction kinetics and many other things, we actually take the concentrations, but here for a general case, this will be not concentration, this must be expressed in terms of activities, and that we'll discuss. So this is the thermodynamic equilibrium constant, which you write as K equilibrium. And so what we get is this delta G0, we can write it as minus RT ln K equilibrium. So you can now write the original equation as the reaction Gibbs free energy is given by delta G0. Instead of that, I'm writing as minus RT ln K equilibrium plus we have RT ln Q. So Q is the reaction quotient. When delta G is 0, so then we'll just have K and Q are equal at equilibrium. So this is a nice compact way of writing the Gibbs free energy change for any reaction. Although we have developed it for a very simple reaction, we'll now see what will happen if we include the stoichiometric numbers for multiple reaction, not only just one reactant and one product. And then we'll see that how we can express the reaction Gibbs free energy in terms of the reaction quotients, and what will happen, what are the conditions that will dictate that the equilibrium has attained.